today, obviously, I'm very greatly honored to welcome our speaker, Dr. Mark Clampin, who is currently the director of the Sciences and Exploration Directorate here at NASA Goddard Space Flight Center. And of course, most of you know this is one of the largest Earth and space science research organization in the world. Like many of his generation, Mark was inspired by the Apollo 11 landing on the moon, but he knew he wanted to work at NASA. Watching NASA teamwork at its best as Apollo 13 recovery unfolded. But he faced a dilemma because he was also attracted to exploring the depths of the ocean, thanks to the work of Jacque Cousteau, the famed undersea explorer. But the pull by the TV star show Star Trek and the possibility of discovering life in the universe hooked Mark to a career in astrophysics. Today, he's going to talk about that journey from UK to USA, from exploring the depth of our oceans to exploring the depth of our universe. How the heck did that happen? Ladies and gentlemen, help me welcome our speaker, Mark Clampin.
So, thank you, and it's good afternoon now. So I'm going to talk about how I ended up as the director here at Goddard, of the Sciences and Exploration Directorate. And I wanted to talk, first of all, just about where I came from. So you probably already understand from my accent that I wasn't born in America. In fact, I was born in Britain, and both of my parents grew up during World War II. And in fact, my father, I remember telling me one of the sort of key moments in his life was when he was about 8 years old, looking up and watching the Luftwaffe flying over on September 15th. And he said, you could tell there were planes, and there were a lot of them because the sky went black, and they were on their way to their first attack on London. After the war, my father joined the Navy and was in the Navy for a long time, and service was a very sort of important value in our family. And in fact, I actually went to a junior school, which was very traditional British school, and we had 4 houses. So they divided the school into 4 houses. And those houses were Churchill, Scott, Oates, and Wilberforce. And some of you may not know all of those names, and you can look them up. But they were basically meant to sort of convey, again, these values of service, leadership, resilience, and also sacrifice. So as you heard a few minutes ago, my early inspiration, especially my interest in astrophysics and space, really came from watching the Apollo 11 landing when I was 9. And I still remember sort of staying up to watch that. And of course, you know, most people from my generation were really inspired by the start of a new generation of space exploration. I was also really impressed a year later when we watched NASA do the Apollo 13 recovery. I mean, for me, that really just captured, you know, what NASA's all about, the teamwork, overcoming numerous problems, and, you know, finally having an outstanding end to that mission. So that's the kind of thing that inspired me when I was a kid. I also was really into science. In the UK at the time when I was a kid, we had a TV show called The Sky at Night, and that was hosted by a very eccentric gentleman called Patrick Moore, or later Sir Patrick Moore. And I would actually see him quite a lot when I was doing my PhD, because he used to visit our department quite often. And he would basically spend a few minutes talking about what you could see if you went out into your yard. But most of the time, he was interviewing academics about, you know, science issues in astrophysics of the day. I also watched what in the UK we called Horizon. Over here, it's Nova. And those shows were always inspirational. And of course, in 1969, Star Trek was the big thing. And I guess I had a kind of a nerdy approach to Star Trek, because the thing that really got me interested in Star Trek was this scene you'd see at the start of every show with the Enterprise orbiting a planet. And, you know, my questions were, well, how do they know those planets look like that? You know, how do they know there are so many? Are there any at all? And at the time, we really didn't know. So this was all supposition, and, creative license on the part of the people that wrote the show. But those questions kind of stayed with me. The other big thing that really inspired me at the time was reading Jacque Cousteau's The Silent World. If you've never read that book, I would strongly urge you to do so. It's a really interesting book about the very early days of scuba just after the Second World War, and watching Jacque Cousteau's TV shows. And at that point, I knew I wanted to do science, and it became very clear to me pretty quickly that doing this was out of the question. I was born with a congenital defect in one of my ears, so I only hear in one ear, as many of you who see me racing to get that key position at the table for meetings know. And so, trying to be an astronaut was just, red flag, no way that's going to get you through the medical. And also, if one wanted to join the service as well, the medical guys just would not allow that kind of medical problem. So the one thing I could do, and we'll talk about later, was diving. And there were no doctors telling me I couldn't do that. So I'll come back to that shortly. When I left school, I did a degree at the University of London, and then I went to Scotland to do a PhD in astrophysics and working on detectors at the University of St Andrews. And St Andrews is in Scotland. It's the oldest university in Scotland, and it's absolutely steeped in tradition. It's 600 years old. And just to tell you how old St Andrews is, this cathedral here, which is a major landmark in the town, and it is a town, not a city, was built in 1158, and it had already been knocked down and ruined through various wars and things happening by 1600. So this has been ruined like this since 1600. And the university is also steeped in tradition. And one of the things I really took away from St Andrews as a very important sort of life lesson was the approach they had to mentoring. So when you become an undergraduate at St Andrews, you get what's called an academic father and an academic mother. So third and fourth year students basically adopt an undergraduate, and their job is to mentor them through their first couple of years at university. And you kind of think this is sort of optional, but in fact, it's a very strong tradition, and it still happens today. And I still have friends I was with at St Andrews who are still in contact with our academic parents. These kind of things build really lifelong relationships. So that's a really useful thing I took away from St Andrews. Mentoring is really important, and it can pay dividends. So I'm going to work my way through the talk now, talking about a couple of themes, and I want to start with science because that's the most important to me. So when I left St Andrews, I was invited to come to the US and do a postdoc with Dr. Francesco Peresce, and he was a famous UV astronomer at Berkeley. He'd been with Stu Barrier's group for about 20 years. And in fact, not just me, but a number of our scientists here actually worked with him or were his students. So he has kind of a long reach into Goddard for that reason. And Francesco was kind of a charismatic figure because his grandfather was Guglielmo Marconi, who we all know was a very famous scientist. So he had just come to the Space Telescope Science Institute to work on the Hubble Space Telescope, which was supposed to launch in, when did it? I think it was supposed to launch in 1986. And I remember sitting in St Andrews just before I was supposed to get on a plane, watching the Challenger accident on the television. And within a day, I got a telegram. And yes, in those days, we didn't have email or any of these kind of things. You got a telegram the day after saying, don't come, wait. So I called him up a couple of days later, and we agreed that he needed to reconfigure the postdoc position and then get ESA to sign off on it. This is European Space Agency. So we managed to do that, and I came out to the US in April to work at Space Telescope Science Institute. And working for Francesco, first and foremost, was a lot of fun. I mean, he was a really fun guy, still is. I still see him when I go to Italy sometimes. And he taught me a number of really important things, and one of those you've already heard. But, focus on the science. And that sounds kind of like a bit of a cliche, but we were spending most of our time building instruments. And he really taught me that it's very easy when you're stuck in the middle of a big instrument program to kind of lose touch with what the primary goals of building that instrument are, what you want to do with it when you finish, and how that should shape the compromises or the changes or the things that you have to do to get the instrument built. So focus on the science is a really important thing for people building hardware. He also taught me this, exploit scientific opportunities. So Francesco was great at building hardware and then figuring out other neat things you could do with this hardware because it was a new and unique capability. And I've got one here that I'll show you later on, which I think is really, really interesting. He also was very big on taking scientific risks, and this is an example. So at the time, we had just found out that stars have something called an infrared excess. And the IRAS satellite, which Goddard was involved with, had just done these measurements of A stars and found a number of them had infrared excess. And ironically, we found this because when we looked at Vega, which was our calibration star for IRAS, it didn't fit the spectral energy distribution that people were expecting for Vega. Instead, it looked quite nice down to about 12 microns, and then the points just went off there. And what that told us is that there's a lot of dust around this star. And then they found that Fomalhaut, a big southern star, had a similar kind of excess, and so did Beta Pictoris. And these were the kind of big three. That's what they've always been known as. But we subsequently found, hundreds of stars that had infrared excesses. Now, the neat thing about this is that the way this infrared excess looks on these graphs tells you that it doesn't go all the way into the star. So you basically are looking at a ring of dust around the star, not just dust around the star. And that was the first indication we had, the first real scientific evidence that there were planets around other stars, because the supposition was that something is clearing out those inner regions. And so that led Francesco to follow up on a measurement that had been done by Smith and Terrell a couple of years earlier to do coronographic observation of Beta Pictoris. Now, Smith and Terrell were the people who did the first discovery observation, but Francesco at the time was essentially kicking his scientific heels, waiting for Hubble to fly, and Hubble had a coronagraph, and he wanted to figure out how you do science with a coronagraph, because very few people had actually done it. What were the things you had to think about when you designed an observation? And for coronography, there are a lot of things, and there's a lot of things you learn as you start to do the observation. Most important one is it takes a very long time, and it confuses a lot of astronomers because they never understand why you spent 2 nights observing time looking at 2 very bright objects, because we think faint object, long exposure, but bright object, short exposure, surely. But what it actually means is you're looking for faint material around a very bright star, and that was a problem we had with time allocation panels for a very long time, trying to convince them that this was a real thing. So what Francesco did was build a coronagraph to play with on telescopes and figure out how to do coronographic science while we figured out how to fix the Hubble Space Telescope by getting it launched. And so he did this observation here. What you're seeing here is the star is under there. We have this big finger that blocks out the light from the star, and then you can see this very faint material in a disk that's around the star Beta Pictoris. And the neat thing about this is that by designing the instrument from scratch using the concepts that were being used in the Hubble instrument, he was able to get the first really good color observations of the disk and understand some things about how the disk looked. And that was published in '86 by Francesco and Chris Burrows. So at the end of a postdoc I did at Hopkins, which I'll come back to, I went to Space Telescope Science Institute, and I got there just before the first servicing mission, and this was a really amazing time to be there with lots of really impressive people. Everybody's heard of Riccardo Giacconi, the director. I also worked very closely with Roger Doxey, and these two between them, I think, really came up with the paradigm of how we do science with the Hubble Space Telescope. And that is that you take data, you run it through a data pipeline, you put it in the archive, and you keep recalibrating it. And that paradigm in 1986 to 1990-ish was really a new thing. And they spent a lot of time and effort getting the ground system put together to enable this to happen. But I firmly believe that one of the great things about Hubble, and one of the reasons it's so successful, is any one of you can go sit at a computer screen, pull down an image from the archive, and you can start doing science on that data immediately because of how well it's calibrated and how well the data is delivered to you. There's a lot of programs where you can't do that, and you still have to sit down and read all the user manuals and spend hours and hours going through how to put the images together and stack them up properly, remove the noise. Hubble really nailed this issue, and it's basically due to the vision of these two guys. I also spent a lot of time working with Chris Blades, and one of the things he really taught me is how to stay cool in an emergency or a crisis. I worked with him on 4 servicing missions, and for the first two of those 4, I was in the servicing mission office at the Institute, so I worked on WIFPIC-2 during servicing mission 1, got to sit there while the astronauts put the instrument in and then check that everything was okay with the science team in real time, so we knew whether they had to leave it in or pull it back out. And Bob Williams, who was the director for most of the time that I was there at the Institute. And I wanted just to say a few words about Bob Williams, because I think he really sort of epitomizes this idea of taking risk in science. So after we had been using WIFPIC-2 after the first service mission on Hubble for a couple of years, people started to realize that some of the programs taking deep images were coming to be a bit of a surprise. They were seeing a lot more faint blue galaxies than they expected. And they were basically seeing a lot deeper, further back than people had really expected to see. And Bob Williams, at a certain point, decided that this was a problem that really needed some heavy-duty observing time, rather than the sort of 10s and 20s of HST orbits that were being used in the programs that were funded at the time. So he put together a group, National Academy style scientific peer review, had people think about whether they should really focus on this problem and put a lot of time and energy into it, or whether it was a waste of time. And they came back and told him that they probably thought it was a bit of a risk and maybe he shouldn't do this. And he thought about it, and I think there's a great quote from George Patton, who said, "The time to take counsel of your fears is before you make an important battle decision. That's the time to listen to every fear you can imagine. And when you've collected all the facts and fears and made your decision, turn them off and go ahead." And that's exactly what Bob did. So he basically collected all the information, decided on the basis of that he was going to go ahead anyway, and that's what he did. And after a couple of hundred orbits, we ended up with the Hubble Deep Field. And that was the first of a number of deep fields, and pretty much changed cosmology. It changed how we think about the deep universe, and it also led to the James Webb Space Telescope. So that was a really seminal moment and a great example of how to take risk in science and get the really big payoff. After I'd been at the Institute for about a year, I was invited to join a science team called the Advanced Camera for Surveys. So within a few weeks of putting the first Hubble instrument in after servicing mission 1, we were already thinking about what we were going to do after servicing mission 2 on servicing mission 3. And you need to do that because it takes a long time to do these instruments. So Holland Ford, who I'd known at Johns Hopkins, invited me to join the team. And the deputy PI was Garth Illingworth, who also you'll see around here a lot. He spends a lot of time advising JWST these days. And Holland was very much the underdog PI. So there were 3 teams competing for this instrument: JPL, Goddard, and Johns Hopkins. And Holland was the Johns Hopkins PI. And he had also been thinking about these deep images that I just mentioned in the context of the deep field, and had concluded that the report advising us on how to build advanced camera was completely wrong. The basic idea of the report was that we should focus on doing very far ultraviolet observations and exploit the angular resolution of Hubble. And Holland, I remember at a science team meeting, had this report, and he threw it in the bin and said, we're not going to do that. Instead, we're going to do deep imaging in the near infrared, because that's where the science is going. And this was even before the Hubble Deep Field had been executed. It was about a year and a bit before. So he put together a really interesting science team, very diverse, a lot of young people, a lot of argumentative young people who were not afraid to really fight for the piece of science that they wanted to do. And Holland also took a very different approach to the science. So when you got these Hubble instruments, if you won one, you got an allocation of, I think, about 400 orbits. And by the time they got put into Hubble and people were starting to do science with them, those 400 orbits have been divvied into 10 or 20 orbit slots. And so, it did a lot of very interesting science, but you could never really concentrate on one program. So Holland, when we joined the team, and when you were invited to join the Advanced Camera for Surveys team, he said, if you join this team, we're only going to do 3 science programs. And we're going to spend almost 2/3 of the time on one of those programs. And if you weren't up for that, then you didn't get to be on the team. It's that simple. And I'll come back to some of the outcome of that in a short while. The other thing he did was prioritize science. And what I mean by that is at the time, if you looked at some of the Hubble instruments, they had lots of modes, lots and lots of filters. It was very hard for the Institute to kind of find their way through the morass of different options to figure out what to offer the general observers when they had call for proposals. And Holland took a very different view. He wanted to do deep near-infrared imaging, period. And if we got a coronagraph, we'd do that too. So we basically designed an instrument designed to have wide field and very high throughput, and everything else we kind of put to one side. So we didn't have a lot of filters. We only had 2 sets of broadband filters and maybe 1 or 2 narrowband filters. And as we went through the program, it was always about the wide field and the throughput. And if anything impacted that, we fixed it. If it didn't, we weren't so quick to deal with it. And he was very good at delegating. So he put me in charge as the detector scientist of delivering 3 focal planes. We had a wide field focal plane, which consisted of 2 2x4K CCDs. And this was the first time we'd ever flown something this big in space, certainly on the NASA side. And then we had a MAMA, which we basically borrowed from STIS, their flight spare, and a 1K by 1K CCD that also came from a STIS design, but which we had to rework. And so we spent a lot of time working with Ball Aerospace to figure out how to mount these 2 CCDs within the tolerances, and then how to package them in a dewar that would get all the heat out of them so we could cool them down to the required operating temperature and operate them without needing a massive radiator on the side of the Hubble. Subsequently, after doing this, Ball won Kepler, so this was their kind of training ground for then putting 40 of these devices on the Kepler focal plane. So this instrument was really dominated by big mirrors and high throughput. During the course of the program, I also became, wearing my other hat at the Institute, the lead for the Advanced Camera for Surveys, and I started looking at things I could do and where I could maybe apply some of these lessons, and there were 2 that really stood out. And anybody who's worked with WFPIC 2 data will remember the famous stealth bomber profile of the images. And when you got delivered these images by the pipeline, you got 4 images, and then you had to put them together and do all the photometric calibration to make everything fit together. And at the time, we had a really smart guy at the Institute called Andy Fruchter who'd just come up with this new way of combining images. And I thought, wouldn't it be great if we could put this in the data pipeline so that when you pulled out an ACS image, that big 4K by 4K image, it was already put together and looked like this rather than coming in little pieces. And so against the better judgment of people like Roger Doxey, who said we really shouldn't be doing this on a brand new instrument that was being rolled out for the first time, we actually put drizzle into the pipeline, made sure we tested it. And when we rolled out Advanced Camera, we had drizzle and people could download fully combined images on day one when they did their science program. The other thing that we did, which I think was ultimately more scientifically important, is make parallel science work. And that sounds very simple. You know, what could be hard? Well, up until Advanced Camera, most of the parallel science capabilities hadn't really worked that well on Hubble. And it was very clear that if you're taking 4K by 4K deep images, you're going to get some really good science with them. And people weren't just using Advanced Camera. They were using NICMOS, which had a new cryocooler. And they were also using parts of STIS. So we wanted to make sure that every time somebody took an image with Hubble or a spectrum that wasn't Advanced Camera, that they were getting for free one of these big 4K by 4K deep images. And also, if they were using Advanced Camera and one of the other cameras, they could get these. And it turned out to be as simple as making a very simple change to the policies and then providing some automation. So if people kind of abstained on doing parallels, it got done for them without them having to worry about it. And the change in policy basically made sure that if it got done for them, the image didn't belong to them. It went straight into the archive as public data. Now, this turned out to be very important when people started doing later deep fields with NICMOS, because NICMOS would sit there staring at the deep field locations for a very long time. And all the time, we were taking these very deep flanking fields with Advanced Camera, and they came for free. So it was a really big scientific payoff in the long run from making what was a very simple policy change. And this is an example of the kind of thing that we built Advanced Camera to do. This is the Hubble Ultra Deep Field. It was the deep field taken with Advanced Camera about a year after we flew it. And in fact, when we come back and think about risk, one of the things we advised the director at the Institute not to do was to start doing this immediately, because we thought that it was very important you understand how your instrument works before you invest hundreds of hours of orbits into taking these kind of pictures. So my science is studying planets, and so I got to be the science lead for the coronagraph that we flew on the instrument. And the coronagraph really did very well. For the first time, we were able to start seeing debris disks. These are the dirt and dust and rocks that are left behind after planetary systems have formed. And we weren't just looking at Beta Pictoris. We started to find them around other stars. And I've got kind of a rogues gallery here. And I think this one was the only one that we knew about before we started. These were all new discoveries that came from the coronagraph on Advanced Camera. And it really kind of opened up our ability to study these disks. And it also did something else. It allowed my colleague Paul Callas, Jim Graham, and a whole team of people, including myself, for the very first time after, at that point, nearly 20 years, to see the dust disk around Fomalhaut. So people have been trying to do this forever with ground-based telescopes and not succeeding, with WIPIC-2 and not succeeding, with STIS, and finally with the Advanced Camera coronagraph with its very high throughput, we were able to see this ring. And contrary to what we thought, it turned out to be a very small, very tight belt orbiting this star, which is located here. And Fomalhaut's one of the brightest stars in the southern sky. And we thought this was such a great discovery, and there were some very interesting things to do with the properties of the disk here at the ANSI, that it would be good to get a kind of template image that we could preserve so that when JWST flies, we could come back and do comparisons over a sort of 10, 15-year time scale. And in the process of doing that, we actually discovered something just here, which is called Fomalhaut B. And over the space of several years, we were able to show this thing was moving. So this was a planet that Hubble was able to image with the Advanced Camera for surveys. and it got a lot of exposure at the time. Now, we're still trying to do follow-up observations of this, and I think it will we'll have to wait until the James Webb is flown to do any better than what we've already done. And of course, this is the James Webb, and this is one of the reasons why I really love working at Goddard, because you can work on programs like this, and I was involved at the very beginning when we were just doing what we call view graph design, all the way through to the delivery of the whole telescope here at Goddard and then its assembly. And this thing actually illustrates for me a very interesting issue I think is very important, especially for people working here at Goddard when you start working with people from other disciplines. So if you're a scientist and you're working with the engineers or with the program managers, communication is very important. So as the observatory project scientist, I spent a lot of time. And the reason I look at this and kind of shudder is because I'm always looking for dust or specks on the mirrors. Spend a lot of time working stray light on these mirrors. So unlike Hubble, where you've got a nice mirror in a tube and a lot of stray light is baffled, James Webb's telescope is just sitting out there, and it can see the whole universe, and anything on the mirror, dust, is going to scatter light. And we spent a lot of time talking with our engineering colleagues about what that meant and what acceptable levels were, especially when we had to do some D-scopes in the sort of 2006, 2008 timeframe. And we used to talk about numbers, and we could never sort of convey the concept that if you have more dust on this mirror, it was going to really impact your ability to see those very first galaxies that formed in the universe. And then one day, an engineer said to me, I really don't get what your problem is, because you just integrate longer. And it clicked. So we went away, and we actually calculated what one of these very first galaxies would look like, and it's around the nanojansky. And then we figured out for different stray light levels, how long would it take to actually get down to 1 nanojansky? And then we went back and said, look, if you go with this stray light level, it's 100,000 seconds. If you double it or triple it, I can't remember the exact number, it goes up to 1 million seconds. So if you want to do 4 colors, that's a 4 million second exposure. And that's what having that extra bit of dust has done to your observation. And after that, we didn't have any more problems talking about stray light. We still had problems talking about the amount of dust on the mirror, but at least we could talk the same language. So sometimes you really have to sort of try the parameter space to find a concept that can convey the scientific impact of what you're talking about so that everybody can sort of buy into a solution. Okay, so I want to change tack now and talk about leadership a bit. And I'm going to start coming back to what you heard at the beginning. So I started scuba diving because, as you heard, I couldn't be an astronaut when I was 13. And at the time in Britain, we had something called the British Subaquia Club, and that was broken up into clubs, and every club basically did its own thing under the guidance of this governing body. So some interesting things. We dived from very small boats, and it was very much a do-it-yourself. So you didn't pay your money, get on a dive boat, and Joe, the dive boat guy, took you to your site, and you dived and came back, and everybody relaxed while they were on the boat. People carry your tanks. It wasn't like that. We were diving from very small boats. We had to essentially train ourselves, organize our dives ourselves, plan them ourselves, and then actually execute the dive and manage the diving ourselves. And this was diving on air. The waters around the UK are not warm, so you have that physiological aspect as well. And for those of you who are divers, these were all rectangular profile dives. Most of the diving, especially in the south of the country, is wrecks. And you go down and you're at one depth for the whole dive, and then you come up. You don't get to do these stage dives that a lot of us do these days. And I used to dive in places like this. So from 13 to when I went to university, I dived with the Clacton Club. I got to the highest level I could at club level, and did a lot of fairly deep diving on wrecks around the UK. And here's a couple of examples. And of course, every one of these wrecks has a story attached to them, which is also very interesting. This one here is Mohegan that ran aground down on the Manacle Rocks in Cornwall. And basically, they just sailed up onto a big rock and didn't realize where they were. This one here is very interesting. This is a submarine called the M2, and it was a converted design. Originally, the Royal Navy in 1914 thought it'd be really neat to have steam submarines with boilers. And when you had to dive, you'd put the boiler out and go down. And after they'd lost about 4 or 5 to really horrific accidents, it dawned on them that, maybe that's not such a good idea. So then they said, well, we'll use these, they were called K-boats. We'll use these K-boats to do some experiments. So this one, they put a hangar on the front and flew a sea boat. Another one, they put a big gun on the front. These two both sunk as well. And this one foundered off of Portland, which is just up here. And this is the kind of thing we were diving. I was diving. Most of them are, below 100 feet. I think this one's about 110, 120. So you get about 20 minutes on the wreck, and you have to do a stop on the way up. The problem in the UK is that it's not a great place to dive if you don't like tidal streams or currents. Currents run extremely strong. They come down both sides of the country, and they kind of meet just around here where this guy is. And so you get to dive at what's called slack water. And slack water is when the tide stops moving. And it's not necessarily high tide. It's when the water stops moving one way and starts moving the other. And you get maybe half an hour to an hour to do your dive. And if you're still down when it starts moving the other way, you're going to be hanging off the shot line to the wreck like a flag. And we'd often get to the bottom of some of these lines that we put down with 50-pound weights on the bottom and find that they dragged off of the wreck, and we weren't on the wreck anymore. So really tough diving. And I'll tell you one other story. We used to dive with fishermen off of fishing boats on wrecks like this. And they would have these big buoys about the size of a basketball. And they'd tie them on the shot line so that when you got to slack water and the water stopped moving, these buoys would just pop up. And that was the moment you knew you could get in, go do your dive, and come back. So you really had to be prepared and organized, because after 20 minutes, you couldn't dive again. So I'm the bane of my family. Whenever we go diving, even today, I'm always there when the boat stops, ready to go in, even if we're in the Caribbean, where you don't have these concerns. But when I went to university, I found that I was one of the most qualified divers in the university clubs. So I ended up spending a lot of time leading expeditions and training people. And we would take expeditions around 20 or 30 students to places, again, on the south coast, down here, to Plymouth, Eddystone Lighthouse, and then the west coast of Scotland, which is all very deep diving with very steep drop-offs. It's actually warmer up there than it is on the south coast, because the Gulf Stream finishes on the west coast of Scotland. So you even get to see coral sometimes. But you learn a lot about leadership when you start doing that. And I had a number of occasions where, as a diving officer and running the dive with 2 or 3 boats, we'd have a couple of people who didn't come back at the required time, and all 20 people would look at you and go, "What do we do now?" So you very quickly, doing this kind of thing, learn about leadership and also a lot about risk management, and I kind of carried that with me through my career. In the mid-90s, I also got to take different kinds of risks. We did a lot of diving in the Pacific on really interesting template desert islands like this one. Got to dive with schools of large barracuda. And in Papua New Guinea, every time you come up to do your stage decompression, you'd be surrounded by lots and lots of sharks. And sometimes we would count several tens of sharks. And of course, the visibility is not good here because the tide is kind of running across the top of the reef. I also saw what happens to the environment, being able to dive in places where nobody else goes and then compare them to places where everybody goes. So coming back to leadership, when I left the Space Telescope and went to do a postdoc at Johns Hopkins, I took all the things I learned about coronagraphs and went to work for the Hopkins astronaut, Sam Durrance, and he was going to fly with the Goddard astronaut, Ron Parisi, on the Hopkins Ultraviolet Telescope UIT payload as a payload specialist, and he too was waiting to go back to work because of Challenger, and the Hopkins and UIT packages have been delayed quite considerably. So I've been working for him for about 6 months, and he got a phone call from Houston and called me up and said, "I'm off, bye, you're in charge." And basically left me with the group. And so for the next 3 years, I had to lead the group building this coronagraph. And it was a slightly different approach to doing this kind of science. Rather than just blocking out the light, we actually built a mirrored occulting mask and pulled that light from the bright star and then used it to do a correction with a tip-tilt mirror initially so that we could take out some of the aberrations due to the atmosphere. And doing that allowed us to get probably the best ground-based image in the visible that was ever taken of Beta Pictoris. We actually found some interesting things in the profiles of this disk that subsequently turned out to be very important when we did Hubble observations and found that there are actually 2 disks there, not 1. So we found an early indication of the 2 disks. We just couldn't tell because we weren't able to resolve with enough resolution what was going on in this region. But we got much closer into the disk than we ever had before. So I worked on that instrument for 3 years, and then when I went back to Space Telescope, Sam Durrance made a deal with Palomar, and the instrument went to the Palomar Observatory and became a facility coronagraph. And one of my colleagues, Rebecca Oppenheimer, who's now at the American Museum of Natural History, and Sri Kulkarni and Nakajima here, started using it to look for brown dwarfs. And at the time, we thought they were brown dwarfs, but nobody had imaged them. And they were able, with this instrument, to get the very first image in the visible of a brown dwarf. This is Gliese 229b. And then subsequently, they got a much prettier picture with Hubble, of course. But this was the discovery image for imaging one of the very first brown dwarfs. And this instrument subsequently went on to make lots of discoveries in this field. They found a lot of new brown dwarfs. And eventually, Rebecca Oppenheimer was able to get it decommissioned when they switched up to something more powerful. And that instrument, which I worked on for 4 years, is now at the American Museum. And you can actually see it. It's one of the exhibits there. Really cool. And as I said, the coronagraph that we put on advanced camera was supposed to be the next step. So going to the launch of advanced camera was really exciting. Unfortunately, it went on Columbia, which subsequently had an accident. And surprisingly, it also launched through clouds, which they told us they weren't going to do. But they did anyway, so it made for a great picture. And this is one of the really neat things about working at Goddard. You can come to work and sit and watch Mike Massimino put your instrument into the Hubble Space Telescope and then press a few buttons and watch to see if it's actually made it in there alive. And this is the post-EVA checkout image. There's Holland Ford there, Pam Sullivan, who's now working for NOAA as the GOES program scientist, George Hartig, one of the great unsung heroes of Hubble, and our team just after we successfully verified that advanced camera worked. And advanced camera was also successful in another way. It was one of the few Hubble instruments that made what we called the Weiler Criterion, which is that it was above the fold of the New York Times, and all 4 of the early release images made it above the fold, which was unheard of. So these were the 4 early release images. I actually selected this one here, which Zsolt LeVay turned into this fantastic, very iconic image. And I was very pleased many years later when Tracy Smith used it as the cover for her Pulitzer Prize-winning poetry book. So I'm starting to get to how I got to be at Goddard. So one of the things when I was working on JWST that I thought was very important was understanding how the Sunshield worked And I spent a lot of time at Northrop with the JWST team watching these deployments being done on something called the IBA. And as a result of that, I ended up spending a lot of time here at Goddard talking to Piers Sellers, who at the time was deputy director and my boss. And he was really interested in this because there were a lot of deployments, a lot of things had to fire, a lot of cables, and he saw a lot of parallels to the work he'd done on spacewalks when he was an astronaut on ISS. So in the course of having these discussions, he suggested I ought to think about applying to be the ASD director, and I did that, and actually was selected, and that's thanks to Piers and his mentorship. And then I worked for Colleen in various roles, first as the head of ASD, and then as the deputy director for many years until she left to join the National Academy. So I wanted to finish up by just saying a few words about why I like being director of this science directorate. And it's really that, I have such a wide range of talented scientists in this division, which is probably the largest space science organization in the world doing space science. And we get to make observations that really push the envelope of science every day. And this is my astrophysics example. This is one of the frontier fields. And this is data that Hubble is taking now to find targets for James Webb Space Telescope. And this can be directly traced back to Holland Ford's original program on advanced camera, because we spent those 300 orbits with advanced camera studying strong lensed clusters, and that's what this is. And you can see all these squiggles here, which are background objects that are being lensed by the yellow galaxies in the field. Basically the gravity of the cluster is bending the light, so you can magnify the images of objects behind. So that's kind of cool, and it also shows you how the science kind of evolves and ties together over time, or it certainly does for me, given how old I am. We also get to do really neat things like orbiting the asteroid Bennu. And this was a picture that was released a few days ago. This is about the size of a tennis court here. I mean, this is really cool. And again, there's all those elements. The science is amazing. This thing's spitting particles at us, and we're trying to figure out why. And that came as a big shock during the furlough when we got told we had to figure out who to bring back and exempt so we could have some scientists, make some informed judgments about how to deal with this, because we pretty much heard about this during the middle of the furlough. And of course, now, there's a lot of challenges. The next step in this mission is to land on this thing, grab a chunk, and bring it back to Goddard. And in order to do that, there's a significant level of risk associated. You can see it's not a nice, smooth surface. It's very rocky. So they're going to be spending the next year figuring out how to do this. So these are the kind of things that I find really exciting, and I really like helping people get to this point with their programs. Or you can surf the sun. This is an image from the Parker Solar Probe I thought was really cool, that was taken a short while ago, and you can see Mercury just here. And in Earth science, we're using lasers to map the ice sheets in the Antarctic, and this is one of the first images from ISAT. So these things are all really cool, and it really sort of is what I get up and come in for each day. And it's great to be able to sort of play a role in setting science priorities, help people nurture new ideas. And I get to work with a really fantastic team here at Goddard across the whole center, and also with the management team here with some really talented people who are committed to service and to the NASA mission. And I find that a lot of fun, and I find it very challenging. I also think that diversity is important, and I found through my career that when we have diverse teams, we do a lot better than when we have a lot of people thinking the same way. And I certainly found that on James Webb. James Webb has a very diverse team. Of course, it's amazing working for John Mather, and I learned so much from his way of asking questions from a direction that I'd never considered. So even things I thought were kind of settled, this is how we're going to do this, John would come in and ask what I thought was a very simple question. And after I thought about it for now, I'd realized that he was actually onto something, and we needed to go back and think again about how we were looking at a problem. But all of these people, make such a great contribution, and I couldn't fit everybody on, so I put the famous, group picture at Goddard. But all these guys, make such a great contribution. And by the way, Randy Kimball was a PhD student for Francesco Parescia, so we still have this sort of family aspect as well. And when I was at Space Telescope, I was always very impressed with Meg Urey, who put together the Baltimore Charter for Women in Astronomy and really pioneered this idea that we really needed to do something about gender diversity. And at the time, because I was at Space Telescope, it was gender diversity in astrophysics. Now I'm very concerned about gender diversity across the whole of our sciences here at Goddard, and making sure that we really have a diverse set of scientists. And just to finish up, I also just want to acknowledge my wife, who, as I said the other day, knows more about emotional intelligence than I ever will, and is continually advising me on how to do things in a more effective way. And she's also another big advocate for gender diversity in astrophysics and STEM, and does a lot of work in that area. And she's a Hubble Space Telescope scientist, works for ESA, so we have this very interesting NASA-ESA dynamic over the dinner table. And I wanted just to highlight one other thing that she pioneered at one of the Hubble conferences, and that's the idea of science as art. And she organizes all the European Space Agency conferences that Hubble has, so they have them every 2 or 3 years. And there was one that was held in Venice, and they invited the German artist to do something. And he decided that it'd be really neat if he could project something on the old buildings in Venice. So what he came up with was to take the catalog of GRISM spectra from advanced camera, a massive catalog of high resolution, or moderate resolution, I should say, GRISM spectra of high redshift galaxies, and then just display them one at a time on the side of the building. And people liked that so much that they were then invited to come and do this in the States. And so he set something up at the American Museum of Natural History, and you can see one of the spectra from advanced camera here being essentially painted onto the big bowl at the museum. So that was very successful, and that continues. And the current show that they organized at the last Hubble conference in Europe is essentially doing a European tour. It's been to a number of big cities now, like Vienna and so on, and is making a lot of headway. And I'll just finish up by acknowledging my daughter, who's always there to keep me grounded. And as you can see, she's kept the family tradition of diving and maybe taking a little risk, but she's also very broad in her talents and also plays for the Baltimore Symphony Youth Orchestra. So I think that's it, but I wanted to finish up by just passing on a few things that I've really found important during my career, not just here at Goddard, but also at Hopkins and then at Space Telescope. And the first one is really for people here at Goddard, and that's network. So as scientists, we know we have to go to conferences and talk to people in the poster hall and network with our colleagues. But we really need to start networking here at Goddard as well. So you need to start talking to the engineers and program managers need to start talking to the scientists. So one of the things I'm wanting to do over the next year is make sure we provide more venues where people can just come and talk about the ideas they have, the science they want to do, and how they might do that with engineers and program managers, and really try to get us all working together on the same page. So network, go out there and talk to someone in a different building and find out what they do. And I know some of our early career scientists said, well, we can't just go over and start walking the corridors. So we're going to try and provide some venues where people can do that. Another one is embrace change. So we all work for the government here, and everything's changing all the time. And you really need, I find, if you can't embrace change and look for the opportunities, you get bogged down very quickly. Just this year so far, we've had a shutdown. We're dealing with a lot of changes that are coming from the implementation of MAP. And you really have to take a very positive attitude to these things and look for the opportunities and things that might come out of them that you can use effectively. I think I've talked enough about stay focused on the science, but when you're on a big program and there's people asking for D-scopes and so on, think about what's really important. What are the things you need to keep to do the science that the instrument or the telescope was built for, and what maybe is not quite so important. And of course, mentor the next generation. And for me, that doesn't mean just being a mentor and talking to people and providing them with guidance. It also means helping them find opportunities. Quite often, people don't find the opportunities because they didn't know they existed, and their mentors may not have thought to guide them to those opportunities. And that certainly happened for me a couple of times. Paresha found me a number of opportunities I would never have thought of thinking about. Piers Sellers guided me towards thinking about management. And Holland Ford did the same thing. Again, he came up to me one day and said, I just realized you're still an associate here at Space Telescope. Why is that? I said, well, they haven't done the promotion yet. So he went back and started talking to people about why the promotion process was broken. And within a year, I had been promoted after being asked to submit the package. So, take a very active interest if you're mentoring. Communicate is another one. And I love this quote by Churchill, courage is what it takes to stand up and speak, but courage is also what it takes to listen. And people say I'm a good listener, but in part that's because I'm just trying to hear what you're saying. But, we really do sometimes need to sit down and actually listen to what people are saying. And, I gave you the example of the James Webb mirror. It took a long time to find a way to communicate with the scientists, between the scientists and the engineers, as to what exactly it was we were talking about and what we really cared about, as opposed to what we were trying to achieve. And once we broke through that communication barrier, we've never had another problem talking about stray light. In the sense of understanding each other, we've certainly had problems about the requirements, but at least we understand what they mean and what the impacts are. So you really need to sort of think around problems and listen to what people are saying. And of course, step up. If you have opportunities, step up and take them. They may not come again. And as I said, we live in an environment in the government where things change a lot. So opportunities come, and you need to step up and take them when you see them, because they may not come again. And then finally, my last word. I was at a conference in Germany many years ago, actually for James Webb Space Telescope. And I do a lot of work for the SPIE, the Society of Photo-Optical Instrumentation Engineers. And we organized this panel because I thought it was important that we got space science program managers and ground-based telescope program managers in the same room, and tried to get them to sort of look at things differently and see if there weren't synergies there. And at the time, some of the big 8 and 10 meter telescopes were having problems with their instruments. And there were similar issues with some of the NASA programs. So we invited Phil Sablehouse to do the keynote. And at the end of it, somebody put up their hand and said, so what do you think's the most important thing about being a manager? And we were all sitting there waiting for him to have some deep thought about how you do budgets or schedules. And he stood up and said, look after yourself, no one else will. He said, if you aren't doing that, then you can't really be an effective manager. And he really sort of lived that, and I certainly took that on board and try and run as much as I can. So with that, I will finish up and take some questions. Thank you. And I'll just leave this up here. So this is a quote from a book that I read when I was a kid by John Fowles called The Magus. And there's this fantastic quote, Utram bibis aquam manandam. And it basically means, what are you drinking, the water or the wave? And I think this really sort of summarizes how I sort of think about life. Thank you.